One of the biggest dreams of all science is to see invisible things. In 2017, that dream comes true. Astronomers link radio dishes around the world to create a detector equivalent in size to the entire Earth. They call it the Event Horizon Telescope. It lets them capture images of two invisible objects, both supermassive black holes in the heart of galaxies. One of those galaxies is our home, the Milky Way.
Today, the Event Horizon Telescope is delighted to share with you the first direct image of the gentle giant in the center of our galaxy, Sagittarius A star.
A ring of light surrounding a darkness. The black hole is called Sagittarius A star. Until the past decade, the mere existence of black holes could only be speculated. Now, we photograph them. In 2019, the first picture of a black hole in the galaxy M87 paved the way for a new understanding of the mysterious core in our own galaxy.
But until now, we didn't have the direct picture confirming that Sag A star was indeed a black hole. This image shows a bright ring surrounding the darkness, the telltale sign of the shadow of the black hole.
In the constellation of Sagittarius, it's the supermassive black hole, just over 27,000 light-years away, in the heart of our own Milky Way galaxy. Compared to the black hole at M87, Sagittarius A star may be small, but it's still the largest, most massive single object within the entire Milky Way galaxy, weighing in with a mass roughly the same as 4.3 million suns. This gives the event horizon a perimeter that would fit inside Mercury's orbit, but so large it would dominate the entire sky if it was inside our solar system.
We see this ring-like shape around the black hole, and the light that falls in makes the shadow in the middle. And this is a very specific feature of the space-time around the black hole. It is a feature of general relativity.
And it's the dramatic resolution of a chain of mysteries. Its story begins in 1933. A young college graduate named Carl Jansky is asked to identify sources of radio static interfering with voice communication. At once, Jansky discovers a steady, mysterious hiss, not of the Earth, but originating from somewhere within our own galaxy. It's a discovery of the ages.
People just said, well, look, this is something new. And one of the first things you do, systematically, is you sweep the whole sky and you say, what's out there? And the name Sagittarius A tells you something, which is that it's the constellation of Sagittarius, which is where the black hole is. And the A tells you, well, that's the first letter of the alphabet. And so when they swept over the constellation of Sagittarius, there's something bright here. Oh, well, that's the first thing we see there. We'll call it Sagittarius A.
The mystery of the Sagittarius A radio source stays unchallenged for decades. But there is speculation. Could Jansky's radio source be the trill of a black hole? By the early 1970s, astronomers find an unusually bright X-ray source in the vicinity of a blue giant star. The trouble is, blue giants are not normally bright in X-rays. It can only mean one thing: the blue giant has an unseen companion. It's called Cygnus X1. Astronomers cannot actually see the black hole, but they do see its terrible effects. Cygnus X1 is eating the blue giant star, a lion devouring its prey. And our understanding of black holes is now one step closer. 1992. Tantalizing evidence for the existence of black holes comes from Hubble Space Telescope. This image of a giant disk of cold gas and dust, 300 light-years across, fueling what might possibly be a supermassive black hole at the core of the galaxy NGC 4261.
We really got earnest about looking to detect the black holes. And then the Hubble Space Telescope, we got better and better. But even with Hubble, we're not close to the black hole. The most we could say is there's big mass concentrations at the centers of all these galaxies. So you keep bringing out evidence to prove the story, but you aren't there yet. And then, something happened in this decade. LIGO was the first to demonstrate right at the strong limit of black holes, close in, that they really exist. Relativity predicts them. And these merging black holes that they found were exactly as relativity predicted. So that was encouraging. This is the next step, is it looks just like what you think it should. The equations predict it. It's there, it has this hole in the center. It has the right scale. It even has the right mass that we measured with our telescopes on Earth, and that is incredible.
By the late 1990s, many astronomers wonder if all galaxies might harbor a supermassive black hole in their core, including our own Milky Way. In work that would lead to a Nobel Prize, astronomer Andrea Ghez and her colleagues found compelling evidence for the existence of a black hole at the radio source Sagittarius A. These are infrared photographs of the core of the Milky Way galaxy, recorded from 1995 through 2018 by the UCLA Galactic Center Group. The red blob is a star called SO2, roughly 15 times more massive than our Sun. Because they're so far away, the actual motions of stars are not something we can actually see within the span of human lifetimes. Yet, something is slinging SO2 in a ballistic orbit at speeds reaching 5,000 kilometers per second, roughly 1/60th the speed of light. What has the power to throw massive stars like SO2 around so effortlessly? Yet, for all their power and mystique, black holes are one of nature's simplest creations.
Based on the theory of general relativity, a black hole only has three parameters. That is the mass, the spin, and the charge. So that is saying all the black holes that we can observe should really be the same.
Every black hole is mass and its spin. They should look alike. The resemblance between the two black holes, M87 and Sagittarius A', confirms an aspect of general relativity.
The main elements of the image that we observe are the ring of brightness that is caused by the gas that's swirling around the black hole, and as it makes its way down, it gets hotter, it emits light, and that's why we see any image at all.
Closer to the hole, the gases become hotter. Corresponding to the hotter temperatures, the gas emits shorter and shorter radio wavelengths.
And by the time you get to the wavelength we observe, about 1 millimeter, you're looking just outside the black hole. What we're really seeing is just the accreting material getting hotter and hotter and glowing as it circles the drain, until finally this inner ring of light that we're revealing is all that's left just before it will spiral in.
The hole itself is inside the dark central region of the photo. Astronomers call this region the shadow of the black hole. The existence of this shadow is a testament to the unchecked power of gravity. Around the hole, the gas is so hot, it changes to a plasma. This is a fourth state of matter, after solids, liquids, and gases. Plasmas form when atoms are heated so much their electrons are stripped away, turning them into ions and a soup of freely swarming electrons. Lightning is a form of plasma. Astronomer C.K. Chan has been working on computer models that examine the immediate conditions around the hole.
But I guess this is the first time we really see what is at the center.
His models predict extreme turbulence in the plasma at the edge of the event horizon.
So we don't really fully understand the physical mechanism yet, but in some numerical simulation, we see those very strong magnetic fields. We can already see this magnetic storm in numerical simulations, and also in observation.
The new picture at Sagittarius A confirms the turbulence predicted in CK's computer models. Event Horizon Telescope researchers are not surprised.
And it's all roiling and turning over. It's chaotic. So it's not surprising that when you bring things into the center of a black hole and force them together, that turbulence occurs there as well. It's a very messy thing. It's not orderly.
The photos from the Event Horizon Telescope are changing our conception of supermassive black holes. Sagittarius A prime is engulfed by a storm in space. A plasma storm.
There will be enormous amounts of wind, circulation. Everything is orbiting around the black hole at very, very high speeds.
Like a hurricane hunter, EHT astronomer Dimitrios Saltis imagines a flight through the turbulence.
And the speed of the wind will get faster and faster and faster as I go closer to the horizon. Actually, when I hit the horizon, the speed of that wind will be very similar to the speed of light. So we're talking about really, really large velocities. Not only is there going to be a lot of wind, but that wind will not be nice and smooth. So it will become more and more and more turbulent as I get closer to the black hole.
Some distance from the inner edge of the storm, Dimitrios approaches the event horizon. It is not a hard detectable surface, but rather an invisible, unmarked boundary.
A black hole has a horizon in the sense that space looks the same as you approach it. And if you get too close, there's no magic warning bell that goes off when you get into it. You would just glide over it, just as you would glide over the horizon on the ocean. There's nothing special that happens, except you're inside. You say, well, that's fun, let's go turn around and get back. Can't do it. You're gone.
Hidden inside the event horizon is an object so small it has no height, width, or depth. Yet it retains all of the gravitational power of every object it ever captured. They call it the Singularity. While the gargantuan scale of an event horizon grabs the headlines, it's the Singularity that holds all the mysteries. One word describes the defining characteristic of a singularity: compaction. Consider the compaction needed to make a black hole like Sagittarius A. This is a vintage 1969 Corvette Stingray. We've just seen one of our experts drive this car into a black hole. It has the weight of most average cars, 1.5 metric tons. Crush it down until it can't be compacted any further. It is now much smaller than it was before, but the car still weighs the same. Squeeze it again until all of its parts, the fenders, the engine, the wheels, all of it, are so compacted, so small, this paramecium could eat it. Now, crush another car, and another. Repeat this process until every car on our planet has been squeezed into this single microscopic particle. Although it takes up a lot less space, this particle still has the full weight of every automobile in the world, all 1.4 billion of them. That's every Ford, Subaru, Toyota, Tesla, you name it, including every Corvette on the planet, now crushed inside. And we're not finished. What about houses, buildings, and cities? Add them to the particle. Add the mountains and the oceans and the air. Squeeze the whole world into the space of this single particle that began with the Corvette. It now weighs 6 billion trillion metric tons. And still, it's not heavy enough. Cram the moon in there, and Mars too. Squash every planet in the solar system. Still not enough. There's only one thing left. Time to crush the sun. Finally, it's all there. The entire solar system, including the Earth and the sun, all inside a microscopic particle. But microscopic is still too big. To become a black hole, this particle must be squeezed further down into the realm of the subatomic, smaller than atoms. In 1899, the German physicist Max Planck proposed a boundary for the smallest size an object can be. This theoretical boundary is called the Planck length. Nothing can be smaller than a Planck length. It's so small, even a single proton in the heart of an atom is about 100 million trillion times larger than one Planck length. Are the singularities inside black holes this small? What happens to matter crushed down to this level is completely unknown. Here, the laws of quantum physics that govern the tiniest, most fundamental building blocks of nature crash into Einstein's general relativity, which addresses the physics of the very large. Black holes are so efficient at keeping their secrets, we will never know if the singularity ever shrinks to the Planck length or beyond.
General relativity, which is Einstein's brilliant creation, which is a theory from which black holes, were predicted, describes what happens as you go in, but not at the very center. At the very center, you're divided by zero, as it were. You can picture like a function that gets steeper and steeper and steeper as you approach zero and then goes to infinity. Well, the formal physics would say it goes to infinity, but that just means we don't know what happens there. Something else has to happen at the smallest radii.
But the things we can see, and have now photographed, the ring of light and the shadow of the black hole in the heart of our galaxy, not only expands our understanding of our place in the cosmos, but demonstrates the power of the creative, inquisitive human mind to probe and learn.
We are explorers, and we want to know our place in the universe, and we want to know what the Earth is and what its past was, and every other bizarre thing that's happening in the universe around us. So I think whether or not humans realize it, we are born to be scientists, and we're born to try to understand the world around us. And I'm lucky enough that I get to do that.
For others, it's the thrill of the chase, the seeing, the measuring, and the questions. Always the questions that pull them forward. It is that insatiable human urge of curiosity that drives our exploration of the most daunting, most secret places of the cosmos. Our Milky Way galaxy and the black hole it keeps in its heart has a story billions of years old. But now, it has a new chapter, the story of the people who lived on a rocky planet out at the galaxy's edge, who learned how to photograph invisible things from far, far away. A black hole called Sagittarius A prime, and that they had the curiosity and the will to do so.
You go from here to there, and there is a much richer and elaborate place, as we know black holes exist. We've seen them with our eyes. We've found it with our instrumentation. That is the most incredible story about this. You can argue about, well, what do they look like? What are they doing? And you'll test this and this. But the fact that you've seen the things, you can't deny it. And that, by me, is the most incredible part of the story.